Okay, hello everyone. Let's go ahead and take a look at the relationship between lines. Now let's go ahead and say that we have two lines in two dimensions. How do these two lines interact? How many different possible ways can they interact? And what would be the algebraic significance of that? So let's go ahead and say, for example, that we have two lines, either in Cartesian form or in vector form. Now, the geometric interpretation of the way that those two lines can interact are four different possibilities. They can be perpendicular to each other, they can intersect, they can be parallel to each other, or they can be coincident. Now, algebraically, how do we go ahead and show that two lines are perpendicular? Well, if we go ahead and take a look at the Cartesian form of the lines, we know that if we take the slope of both lines and multiply them together and we come up with -1, then we know that the two lines are perpendicular. But let's say, for example, that we have the lines in vector form. How do we go about showing that two lines are perpendicular? Well, we take the directional vectors and we take the scalar product of those directional vectors, and if it's equal to 0, we know they're perpendicular. Now let's go ahead and take a look at the next possibility, is where the two lines actually intersect. Now, if the two slopes are not equal to each other, then we know that they intersect. If, say for example, the scalar product of the two directional vectors is not plus or minus 1, or one of the directional vectors is not a scalar multiple of the other directional vector, of course k not being equal to 0, then we know for a fact that the two lines intersect. Now let's go ahead and take a look at the parallel case. This one says, from the Cartesian standpoint, is that if we know that these two slopes are the same, then we know they're parallel. But in addition to that, we also have to make sure that the y-intercepts are also different. Now, if we go ahead and take a look at that from the vector equation perspective, we know that the scalar product of the two directional vectors has to be equal to plus or minus 1, or we know that the directional vectors are going to be scalar multiples of each other, of course k not being equal to 0, and we have to know that p sub 1, which is the position vector of one of the lines, does not satisfy the other line. Okay, with the coincident lines, we know that the two slopes have to be the same, as well as the y-intercepts. In this case as well, we know that the two directional vectors of the lines, if we take the scalar product, it has to be equal to plus or minus 1, or the two directional vectors are scalar multiples of each other, of course k not being equal to 0, and p sub 1, which is the position vector of one of the lines, satisfies the equation of the other line. And there you go. That's how we can go ahead and determine algebraically, given either a line in Cartesian or vector form, whether a line is perpendicular, whether it intersects, whether it's parallel, or whether it's coincident. Now, of course, this is only in two dimensions. What we're going to do is we're going to take a look in class as what happens with the three-dimensional case. And I'll go ahead and show some of that to you in class. But I also go ahead and invite you to take a look and think about how you would go about determining, from an algebraic perspective, all the different geometric interpretations of the way that two lines can interact in three-dimensional space. Okay, so we'll take a look at that in class so that we can discuss this a little bit more and make sure that everybody has a very good understanding of how we can look at two lines in either the Cartesian or the vector form and determine algebraically what the geometric interpretation of those lines will be. Okay, so I'll see you in class the next time. Bye-bye.